I call it fusion grade duct tape. You may look at it like similar to duct tape or adhesive tape, but the difference is that it's not adhesion, it's fusion. Why can't you make the handheld device that applies thermoplastic tape? If you stop, the lamp shuts down. If you move faster, it starts to get more power. So many ideas we have about the use cases. So we start with repair. Why don't you put it on a moving robotic platform and then you can do the automatic layup in the mold? I had this idea, I thought about it for many years, and this is where it comes from. So you know how FDM was invented. Was invented by an American engineer, Scott Crump. And I don't know if it's true or not, but the story tells that he was trying to make a toy for his kids with using the glue gun. So he took the glue gun and tried to draw something. And then he realized that, hand is not, you can get the tolerance and you can get the synchronization. So he decided, why don't I put it on a gantry frame? Yeah. So this is, the story tells this is how FDM was invented. And we were doing in this 3D printing company, what we were doing is also material extrusion, but embedding continuous fiber into the plastic flow with a certain technology, how to make it happen. And I thought, maybe why don't you have the pen where you can also have the fiber in? This was the idea. That then I start questioning, like, why? And the immediate idea was repair. So you got this plastic repair industry, which have very simple tools. So you had kind of a hot air glue gun. So you have a hot air gun, then you have the plastic filament, and then you have a small thing to
smoothen it.
To smooth it, to apply. Then there are some semi-automated solutions how you can apply in the industry. And I thought, it might make sense if you also do it with fiber, because then it can create much like stronger connecting joints, stronger connection points. And then actually I tried this concept. We had on one of our corporate events back then in Anisoprint in my 3D printing company. I bought a bunch of hot glue guns, and I drilled the holes in the nozzle so I can just pull the fiber in, and then you like co-extrude this way, like the fiber and the glue, and then the teams were building bridges with I think that was some natural fibers, like something very simple that you can buy on the market, and hot glue gun, and it was fun. But then I start thinking, because I saw obviously certain issues with this approach, and mainly in the use cases. So you can make it work. It would work, but if you, for example, if you want to fix the crack, so with the fiber needs to go across the crack, not along the crack. It doesn't make sense. So in this case, you will need to do like zigzag steer it. And then the problem is with this, that you need to somehow hold the fiber.
You need tension, right?
You need to make tension on the
steer,
on the turnarounds, but this may be still valid concept. But then we came up with another approach: is why don't we use tape for that? And why? And because in this case you can use cross-ply tape. So yeah,
Yes. Okay. Yeah.
you have like 2 layers.
So is that UD?
UD and
So
90.
backing and then there's a 90 on
Yes,
it.
yeah, and actually this is the standard product. These tapes is PP glass, PE glass. They are widely available and actually very cheap.
Yeah.
So this cross-ply 2-3 layer PP glass tapes.
Yes, PPM glass. Okay, PPM glass.
PP glass,
Cheap.
so less than $3 per kilogram.
Okay, yeah. So
Big market, yeah, it's available, and we thought, how do you apply this tape? What do you need to apply this tape? And obviously, everyone knows in composites, I think there is AFP, right? So if you want to apply thermoplastic, yeah. So the thing is, what I found interesting is that you have thermoset and you have thermoplastic, right? Two worlds, right? And the thermosets have this advantage that you can process them at room temperature, so you can lay up with hands, either like the fabric, the preform, and then you impregnate it, or you apply prepregs, which are also soft at room temperature. But for thermoplastics, you can't do that. At room temperature, the prepreg is stiff. And if you want to apply it, you need to keep it at a very precise, precise temperature. It's hot and it needs to be at a certain temperature. So how do you do it with hand? So the obvious solution that you need automation for that. You need to be able to precisely control, to have the thermal control and the layup speed. Everything has to be consistent, the temperature and the layup speed. So you need a robot. But then I thought maybe not necessarily. So why can't you make the handheld device that applies thermoplastic tape? And actually something like this exists for marking. You know, they have these. There is a big company called Leicester.
Okay.
I think they're, despite their names, it sounds British, but they're from Switzerland.
Yeah, I know them. Okay, yeah.
Yeah, they do this tape marking, welding, like big, rather big machines on wheels, and normally they use hot air. But I thought, why do you use hot air? Hot air you cannot really control. Yeah, because if you want to change the temperature or you want to change the flux, with hot air it's hard to.
This lag is what.
Yes,
right?
yes, it's inertia.
Faster,
yeah.
That inertia, you're not getting the energy in.
Yes.
Okay.
And what's fast? Yeah, what are the heat sources we use for to heat the material? And yeah, we know it from AFP. Also, we have IR lamps, like halogen lamps, and we have laser. Yeah, laser has higher power heat flux, higher power output, so you can move faster. But for the handle tool, maybe you cannot move that fast, so you don't probably really need it. So we thought, again, then the only thing that should work is IR lamps, and they are actually very quick response, so you can dim them very quickly. And the idea is that you have this hand tool, and you apply the tape as long as you move it, and then the motion speed. You have like the rollers which rotate.
An encoder there, right?
Yeah, and then you couple the motion speed to the lamp
Yeah.
power. So
The power law and
if you stop, the lamp shuts down. If you move faster, it starts get more power, like generate more heat, and then you can indicate to the user, right, when he is within the right process window for not too slow, not too fast. But later we found out that this process window can be quite large. And then you need basically two things, right? You need to melt the tape, and then you need to consolidate, to apply pressure. And so with heating, there is a solution. So you couple speed to power, and then we start doing tests on the test bench. So how the tape is melting, at which speed, how much power do we need for this, like standard tapes, which lamps we can use, and so on, and seem to be working. And then the next step is compaction, and also here the solution is pretty simple. So you get the roller, and then you get the spring, and when you put the machine on the surface, the spring is pushing it on the top. But then when you apply your body weight to it, so you push the spring down, and then when the back of the device touches the surface is when there is enough force, so then you can move. And these are little simple things how to enable both the temperature and pressure control. And we've been able to put it in a relatively small device. It can be made smaller, but we probably don't need to make it smaller because we still need pressure. And weight actually helps to put more pressure. And we put it in this proof of concept, and surprisingly, from the first attempt, it worked surprisingly well. And I call it the fusion grade duct tape, right? So you may look at it similar to this duct tape or adhesive tape.
Yeah.
But the difference is that it's not adhesion, it's fusion.
Yeah.
And what is the main advantages of fusion compared to adhesion? It's a stronger bond. So normally you will get, in case your heating and pressure is correct, you will have a high strength compared to the adhesive that you can use in tapes. It's also, and then it does not degrade over time. Mm-hmm. Adhesive bond, if you apply under sun and moisture, if you put the adhesive tape on the car bumper, then a few days it rips apart. And with fusion, no, it will stay as long as the plastic stays. So it's much stronger, much more reliable, much more lasting bond. And
I mean, you build a machine that you're controlling some important variables. So the speed is adjusting the energy going in through your infrared heater, right?
Yes. So there is speed and power.
Yeah.
And speed and power convert into temperature.
Yeah.
So more power, more speed, one temperature. Less power, less speed, maybe same temperature. So they are coupled into this temperature variable.
Absolutely.
Yeah.
So then the next variable you have is pressure.
It's pressure.
And you're controlling pressure through when the spring bottoms out, you meet the minimum requisite pressure.
Yes.
Yeah, so these are two big variables. And I take it, the roller itself, is it like a hard roller that you're using, or is it like a semi-conforming roller?
In this proof of concept, it's a hard roller.
Hard roller.
So of course, it's a proof of concept. We don't want to test many concepts, many features at the same time. But what I like about this is how many things you can imagine, you can implement. And this concept may be recreated, implemented into different devices for different applications, use cases, different industries.
And I was curious about so if you had a laser in there, while laser has got really good power density, the challenge with this laser is just health and safety. So anyone you bring that around, you need the goggles and you need to evacuate the environment. Infrared is a lot more forgiving.
Yes.
From a health and safety point of view.
Definitely.
So are there requirements for someone to wear something while using it, or is it just localized heating so it doesn't matter too much?
No, it doesn't matter. First of all, when you work on the surface, you don't even see much light because it's enclosed, it's under the hood. You just don't want to put it up and face in someone's face, but anyways it won't work like that because it needs to move.
Need the pressure and
it needs the pressure and the motion for the lamps to turn on. Laser is dangerous, not just because of the
it's the eyes
for the eyes, but if it's very easy to overheat the surface with laser, and we've seen it because, a little out of the process, and you got fire. With lamps, there is of course still the risk of overheat, but it's much lower, and you probably won't get that much problems. And anyways, like power-wise, it doesn't matter because power-wise you need same energy, right, to melt. So we currently in the proof of concept we use 2 1 kilowatt lamps. So because one is for heating the substrate, one is for heating the tape. So they're like this. So tape goes here and substrate goes here.
So both surfaces are preheated before.
Yes, both surfaces are preheated, so you obviously need to also preheat the substrate.
And what resins are you getting right now up to temperature? So you mentioned earlier polypropylene.
So it's currently we work with low temperature, so mainly PP, PA, but we use actually thick tapes, like half millimeter tapes.
It's very
half millimeter, 50 millimeter wide. So and this energy, this power is enough. For this kind of tapes to really melt in. And although we still need to work on the process, but sometimes we able to achieve the bond quality. It's my best test. You just try to tear it with your hand. No, you can't do it. If you really try, you split half of the tape, so the fibers stay on on the substrate. You just split the tape into two halves. So the bonding, the possible bonding quality. Yeah, sometimes we at the moment we do not always achieve this level, but it's possible, and we are slowly learning about these regimes.
Yeah.
And because these are different regimes for different materials, it's for radiation, it's also color that matters. If you have black, then it's one constant for emissivity, right? If it's white,
So emissivity varies. Polymer type.
Polymer type,
fibers
color.
you have in it.
Fibers, yes.
Yeah.
But we can use, I think, also high temperature polymers, but then probably you need a thinner tape. So you go to like standard 0.1, 0.15, so UD, like standard UD tapes.
I mean, based on what you're doing, what would be the use? Because definitely polypropylene makes sense. Maybe going up to PA6. What are the use cases you're going after? Who are these markets?
Oh, there are so many ideas we have about the use cases. So we start with repair, MRO. So in different fields, what I think like most obvious is board repair, especially if we're gonna soon have more thermoplastic boards. I think we haven't tested it, but it may still work somehow with the thermosets as well. But we haven't tested it yet.
So Vitrimer type of thermoset.
Yes, maybe. Yeah, right. So board repair. Actually, all this collision industry in automotive, so plastic repair, their current proof of concept maybe doesn't fit very well because it's a little bit bulky and you cannot really steer it and fit into the small zones like in between the ribs. But we made a short video. You can watch it on our YouTube channel. So how you can use it for repair of the car bumper. So we got like the bumper with a crack like this. So anyway, you do the surface, so you do this like standard plastic, but then it's not strong. So and from inside you just put a few tapes.
Yeah.
From the inside, so you fix it from the inside, and then you smooth it
on the outside. Yeah.
From the outside, and it's already stronger bond, and it's actually stronger than they have these like standard solutions with metal inserts with metal.
So you have a comparison of how standard is, right? Where they put these metal inserts and then they clip it out.
Yes.
And what you're having is you're repairing it from behind.
Yes.
And you're getting a stronger bond.
Yes, it's a much stronger bond. But then you can imagine many surfaces, because which doesn't have this much geometric limitations, like all this for trucks, all these like spoilers and big plastic parts for sandwich panels.
And I'm wondering, thermoplastic is the obvious one because the material allows for it. With thermosets, you have some companies such as L&L, they make these thermoplastic ready adhesives. And I do wonder, could you put that, like you have the adhesive on something like a glass backing, and then heat and temperature, what they're doing is you put it in an oven at 100, get it to 150, cycle it down. You could do thermoset repair.
Maybe, I think
so. Or even if you're just heating it, snap your thermoset or whatever. Maybe there's opportunities.
Yeah, maybe you can first apply this adhesive, and then you activate it with the machine and place the tape. We will try it. That's a very good idea. And so repair but then beyond repair, you can do like local stiffening. So if you have some, or connecting sheets, so you get two plastic sheets. How do you and you want to put them together? It's very simple. You just tape them like this, and then you can easily connect plastic sheets that then bend and connect, or then maybe for this like booth building industry, instead of using screws and wood, so you can switch to like plastic and these kind of tapes. Maybe you can also build. So we use it as a layup tool for in the mold, and we just maybe 1 hour ago with my colleagues we've discussed why don't you maybe you just put it on a moving robotic platform, and you can do the automatic layup in the mold. Maybe even for wind turbines or boats, you have robots that go into the mold and laid up. So there are many ideas that we discussed, that we have. You can also use it maybe for somehow like simple winding. So you get just the rotating mandrel, then you just put the device on the mandrel, and then you
locally
move it like manually. So this.
Sorry.
This must be.
Oh, that's the alarm. Let me stop it. But we can. You have to go in a couple of minutes.
I
can
may,
bring it close. But that's really good though. So clearly you have a lot of applications, and you're looking at business to consumer and maybe business to business too. It's both.
Business to consumer maybe. So there's what we're looking for is to it's kind of, I would say it's a professional tool. So I don't know, maybe there will be a household use case like
eventually,
but it's more like we look into the professional tool for repair shops, for repair technicians, maybe some manufacturers. So what we are currently, because as I say, I have so many ideas for applications, but we need to look at the market, at the reality, what is really working, what is really needed, what really solves.
Where the pain points are.
Where is the pain point, and then after we define these few pain points, we first need to start with something. So we choose one. We choose one which we think has the highest potential. Then we design the product. And the first product, and then we can later, if it works, if it scales, we can came up with more products for more industries. So that's why now we decided that we want to do sort of the beta test program. So we
you want to get some data.
Yes, we want to get feedback.
Absolutely.
We want to get feedback, what works, what doesn't work, feedback on the technology, feedback for some features, or what works, what doesn't work, which materials work. Then we collect this data, and then we can formulate the product requirements. That's what we try to do. So now we are looking for beta testers, and then we can provide the prototype system for them, similar to this first proof of concept, but with some improvements, some changes. We are currently finalizing this first EVT, as they call it, evaluation batch, and which we want to distribute to beta users. to get their feedback and to see where are we moving next.
Nice. I'm definitely looking forward. I mean, I've seen the LinkedIn posts and it definitely stoked my curiosity. Well, I'm like, I would love to play around with one of these. So looking forward to see.
Sure, you're welcome. You can have one.
I'm definitely looking forward to see what comes out of it, and yeah, at some point, yeah, bring one to the West, and yeah, definitely would be good to play around with.
Yeah, you can make a review. Honest review.
Yeah, thank you very much, Fedor. Really appreciate your time.
Thank you for your time.